This video contains the solutions to the Lagrange multipliers practice problems. So this is what a typical Lagrange multipliers problem will look like. You've got your function f of xy, which we call the objective function. And again, the idea here is that the objective is to maximize or minimize that. And then you have a constraint, which restricts the points that you can consider. So if we call the objective function f, which we've done here, and the constraint can be written in the form g of x comma y equals 0, then the max and the min occur when the gradient of f is parallel to the gradient of g. And the way we write this is we set the gradient of f is equal to some scalar multiple, which we call lambda, times the gradient of the function g. Now in practice, this gives us several solutions that we can solve. So the gradient of f, remember, is the partial derivative with respect to x, comma the partial derivative with respect to y, and so this would be lambda times the partial derivative with respect to x, lambda times the partial derivative with respect to y. So the first thing we're going to have to do is to find these partial derivatives. So f sub x is 3, f sub y is 4, g sub x is 2x. Now remember, if we're going to write this as g of xy equals 0, we have to do one slight manipulation here and rewrite this as x squared plus y squared minus 100 equals 0. But that doesn't affect my partial derivatives. Getting back to the partials, g sub y is 2y. So this gives us the equations 3 equals lambda times 2x, and 4 equals lambda times 2y. And now it looks like we've got 2 equations and 3 variables, so we're going to get stuck. But remember that the constraint is itself one of our equations. So x squared plus y squared equals 100 is also an equation that we can use here. So what we're going to do here is solve this equation for x. So we get x equals 3 divided by 2 lambda. And here we get y equals 4 divided by 2 lambda. And so when we plug into x squared plus y squared equals 100, we get 3 over 2 lambda squared plus 4 over 2 lambda squared equals 100. And we're going to be able to solve that equation for lambda. So that gives us 9 over 4 lambda squared plus 16 over 4 lambda squared equals 100. Multiplying both sides by 4 lambda squared, we get 9 plus 16 equals 400 lambda squared. 9 plus 16 is 25. Divide both sides by 400, we get lambda squared equals 25 over 400, also known as 1 over 16. And so if lambda squared is 1 over 16, then lambda is going to be plus or minus 1/4. Plugging this back into the equations that we have for x and y, x is going to be 3 over 2 lambda, and if lambda is positive 1/4, then that's going to give us 2 solutions, which are that x equals plus or minus 6, and then when y is 4 over 2 lambda, that's going to give us y equals plus or minus 8. So our 2 points that we get are 6 comma 8 when lambda is positive 1/4, and negative 6 comma negative 8, that's when lambda equals minus 1/4. So now, which one's the maximum and which one's the minimum? Well, for that we plug back into our objective function. So f of 6 comma 8, that's 3 times 6 plus 4 times 8, which is positive 50. And if we plug negative 6 comma negative 8 in, we get minus 50. So that must mean that the positive value is our max, and the negative value, that's our min. All right, same kind of question. Again, the setup is that our x partial derivative of f will be lambda times the x partial derivative of g. The y partial derivative of f is lambda times the y partial derivative of g. And again, we have to manipulate the constraint just slightly so that it looks like g of x comma y equals 0. So in this case, my x partial is negative 8x, and that's supposed to equal lambda times my x partial of g, which is 2x. And then fy equals lambda gy gives me 2y equals lambda times 4y. Now we want to be a little bit careful here not to just divide both sides by x, because if I, for example, take this equation and add 8x to both sides, I get 2 lambda x plus 8x equals 0. And if I factor that equation, I can factor out a 2x, gives me lambda plus 4. And that means that either x equals 0 or lambda equals negative 4. And so both of those are possibilities to make this equation true. Similarly, over here in this second equation, we get 4 lambda y minus 2y. I can factor out a 2y. That gives me 2 lambda minus 1. and that gives me two possible solutions, y equals 0, or lambda equals 1/2. So now let's go back to our first set of solutions and consider the possibilities. What if x equals 0? If x equals 0, then we can go to our constraint, which would tell us that 0 squared plus 2 times y squared minus 4 equals 0. So 2y squared equals 4, y squared equals 2, and so y equals plus or minus the square root of 2. And that seems to work, right? So in the second case, we would not get that y equals 0, but instead we would get that lambda equals 1/2. That makes all three equations work out, and so that gives us two potential places where we can get our max or our min, at the point 0 comma the square root of 2, and the point 0 comma negative the square root of 2. Okay, what if lambda equals -4? That's the other possibility from my first OR statement. Well, if lambda equals -4, then in my second pair of possibilities, that means lambda is not equal to 1/2. This doesn't happen, and that means that y would have to equal 0. So if lambda equals -4, then y has to be 0, and then similarly we can solve x squared plus 2 times 0 squared minus 4 equals 0, x squared equals 4, x equals plus or minus 2. So that gives us two more points where my maximum and minimum value could be 2 comma 0 and -2 comma 0. So now what I need to do is take all four of those potential solutions and plug them back into my objective function. Whichever one gives me the biggest answer, that's where my maximum is. Whichever one gives me the smallest answer, that's where my minimum is. So here's my objective function and my 4 points. So I'm going to plug all of these points into my function f and see what I get. When I plug 0 comma the square root of 2 in, I get square root of 2 squared minus 4 times 0 squared. That works out to be 2. I get the same thing when I plug in the point 0 comma -2. When I plug the point 2 comma 0, I get 0 squared minus 4 times 2 squared. That's -16. And again, I get the same thing when I plug in the point -2 comma 0. So that means that my maximum value occurs twice at the point 0 radical 2 and the point 0 negative radical 2. So that's my max. And then my minimum value, the lower value that I got here, happens again twice at the points 2, 0 and -2, 0, and the minimum value is -16. Okay, so this is a slightly different way, problem, a slightly different way to see Lagrange multipliers example, but this is more of like an application. So in this case, we want to find the point on this circle that is closest to the point 3 comma 4. So the idea is that we have this circle, we have the point 3 comma 4, and what we're interested in minimizing is the distance between a point on the circle and the point 3 comma 4. So some point x comma y on the circle to the point 3 comma 4, that's the distance d that I would like to try to minimize. So an expression for that distance, just using the distance formula, is x minus 3 squared plus y minus 4 squared. And so that's going to really be my objective function, that's going to be my f, that's what I'm going to try to minimize. Now, it turns out that we can make our lives a lot easier, and there's a hint on the worksheet about this, that when we want to minimize a square root, we can do it by minimizing the square of that square root. So we can minimize the distance by really minimizing the square of the distance. And that's because the square root function is an increasing function. So if I were to minimize the thing that I'm taking the square root of, then I'm minimizing the square root. So that's really going to be my objective function, which is going to make the algebra and the arithmetic in this problem much, much easier. And now the point, though, can't just be anywhere in the xy plane. I mean, if it could be anywhere in the xy plane, then the minimum would be at the point 3 comma 4, just make the distance 0. The point is constrained to be on that circle. So this equation here, x squared plus y squared equals 4, or really when I solve it for 0, that's my objective function. Sorry, that's my constraint. G of xy equals x squared plus y squared minus 4. And now it looks more like a typical Lagrange multipliers problem. So our equations are going to be fx equals lambda gx, fy equals lambda gy. My x partial derivative is going to be 2 times x minus 3. My x partial derivative of g is just going to be 2x. And my second equation is going to be 2 times y minus 4 equals lambda times 2y. So now we have to solve this system of equations, and here it's different depending on each situation. Here what I'd like to do is solve both equations for x and y, and then substitute into my constraint. So when I do that, I get 2x minus 6 equals 2x lambda. Remember, I'm trying to solve for x, so I'm going to add 6 to both sides and subtract 2x lambda from both sides. I get 2x minus 2x lambda equals 6. Factor out an x, so I get 2 minus 2 lambda equals 6. Divide both sides by 2 minus 2 lambda, I get 6 divided by 2 minus 2 lambda, and I can simplify that slightly into 3 divided by 1 minus lambda. Similarly, in this equation with y's, I get 2y minus 8 equals 2y lambda. 2y minus 2y lambda equals 8. Factor out a y, I get 2 minus 2 lambda equals 8. So y is going to equal 4 divided by 1 minus lambda. Substituting those into my constraint, I get 3 divided by 1 minus lambda squared plus 4 divided by 1 minus lambda squared equals 4. So that's going to be 9 divided by 1 minus lambda quantity squared plus 16 divided by 1 minus lambda quantity squared equals 4. Let's continue this on the next slide. We've got a common denominator, so that's 25 divided by 1 minus lambda squared equals 4. Multiply both sides by 1 minus lambda squared. Divide both sides by 4. Take the square root, so we get 1 minus lambda equals plus or minus 5 over 2. That gives us two possibilities. If 1 minus lambda equals positive 5 over 2, then that means that lambda equals negative 3 halves. And if 1 minus lambda equals negative 5 over 2, then that means that lambda equals positive 7 halves. Now we have to go back and remember what x and y were. X was 3 divided by 1 minus lambda. So if lambda is negative 3 halves, y was also 4 divided by 1 minus lambda. So if lambda is minus 3 halves, then x works out to be 6/5, and y works out to be 8/5. And if lambda is positive 7 halves, then x works out to be negative 6/5, and y works out to be negative 8/5. Now again, thinking about our picture, so we could plug both of these into our objective function and actually compute the distances. But thinking about our picture, remember we've got this circle, and then we've got the point 3, 4. The 2 points that we found are 6/5, 8/5, which is right around there. And then the point we found over here is negative 6/5, negative 8/5. And if we think about the picture, what we're seeing is that the point negative 6/5, negative 8/5 is actually the point that's farthest away from 3, 4. That's my maximum distance. And so the point that minimizes my distance, the point closest, is the point 6/5, 8/5. So just by drawing a quick little picture, I can tell which solution is correct. All right, this is another application of Lagrange multipliers problem. These are called Cobb-Douglas equations, and the idea is that we want to use this expression here, which represents production, and we want to maximize that subject to this constraint, 4L plus 2K equals 50. So my objective function, which is f of Lk equals 32, L to the 0.6, k to the 0.4. And by the way, if it makes you more comfortable to change the L's and the K's to X's and Y's, that's totally fine. I'm just going to keep them L's and K's. And then my constraint function is g of Lk equals 4L plus 2K minus 50. So Lagrange multipliers would tell me that the L partial of f has to equal lambda times the L partial of g, and the k partial of f has to equal lambda times the k partial of g. So what's the L partial of f? Well, the L partial, the 32, is going to be a constant multiple. The k to the 0.4 is going to be a constant multiple. And then I bring down the 0.6, subtract 1 from that exponent. That gives me k to the 0.4 times 0.6 L to the negative 0.4. And that's supposed to equal lambda times the L partial of g, which is just 4. And then f sub k equals lambda times g sub k is similarly going to give me 32 times L to the 0.6 times 0.4 times k to the negative 0.6, which equals lambda times the k partial of g, which is 2. All right, let's clean these up a little bit. So L to the 0.6 divided by k to the 0.6, that's L to the 0.6 over k to the 0.6, using that negative exponent. Divide both sides by 2, and multiply 32 times 0.4 divided by 2 is going to be 6.4. And that equals lambda. So I'm going to take that expression for lambda and plug it into my other equation. So 32 times 0.6 is 19.2. K to the 0.4 times L to the negative 0.4, that's K to the 0.4 divided by L to the 0.4, equals 4 times lambda. Now lambda equals 6.4 times L to the 0.6 divided by K to the 0.6. Now what I'm going to do is multiply both sides by L to the 0.4 to get rid of the fraction on the left. And I'm also going to multiply both sides by K to the 0.6 to get rid of the fraction on the right. So that's going to have the effect of getting rid of all the fractions and also making those crazy decimal exponents go away as well, because K to the 0.6 times K to the 0.4, that's just K to the first. So we get 19.2 times K equals 4 times 6.4 is 25.6, and then L to the 0.6 times L to the 0.4, that's just L. So let's divide both sides by 19.2, and 25.6 divided by 19.2 turns out to be 4/3. So K equals 4/3 L, and now I'm going to substitute that into my constraint equation. So we just figured out that K equals 4/3 L, and so that means that in this equation I can replace K by 4/3 L. And now I can solve for L. So I get 4L plus 8/3 L equals 50. 4 is 12/3, so that's 12/3 L plus 8/3 L equals 50, so 20/3 L equals 50. So L equals 50 times 3/20, which is also known as 7.5. And then K equals 4/3 times that, which is 10. Now that's the only solution that we got, so that must be the maximum that we're looking for. So the maximum occurs at L equals 7.5 and K equals 10.